Hi guys, my name is Tensor. Welcome to part 6 of our Golang blockchain tutorial series. In this series, we're going to add signing, verification, and locking to our transactions. And to achieve this, we need to integrate our wallet module into our blockchain. Before we get into the blockchain code, we need to create a validate address function for our wallet module. And the idea is that we take in our address, which is a string. We then convert it back into the full hash by passing it through the base 58 decoder, which is the reverse of what we did with this address function up here. Rip out the version portion, which is the first byte or the first two characters of the full hash, and then also take off the pub key hash portion so that all we have is the checksum. And then we can take the pub key hash, attach a new constant to it, and then pass it back through our checksum function to create a new checksum. And then we can use the bytes compare operator to compare the actual checksum with the target checksum. And if they are equal, then it will come back as 0 and will return true from this function. Now, to really understand validation, locking, and signing, let's walk through how transactions work again. So first we create our Genesis block, which has a single input and a single output. And when a user mines the Genesis block, they get the reward in the output. So in this case, user A has mined the Genesis block. Therefore, user A owns the output with the 100 tokens inside of it. If user A then decides to send 10 tokens to another user, let's call him user B, then another block is created for the next transaction in which the input references the original output with the 100 tokens in it. And a new output is created for user A with the 90 remaining tokens inside of it, and another output is created for user B with 10 tokens inside of it. In this case, the original output becomes spent, and now we have two unspent outputs, one which is user A's and another one which is user B's. Now let's say that user B sends 10 tokens to user C, effectively removing any tokens that user B owns. This will create another block where we have an input and a single output. Because user B owns no more tokens, he doesn't get another output inside of block 2, and instead we just have an output which is unspent and assigned to user C. This idea of digital signing or digital signatures comes into effect to guarantee that the data can't be modified while it's being transferred from one sender to another, and that the data was sent by a specific sender, and that that sender can't deny sending the data. So when user A sends 10 tokens to user B, we know for sure that user A sent those 10 tokens. And the 10 tokens cannot be modified while they're in transit to user B. And there's no way that user A can deny that he's sent the 10 tokens to user B. The Genesis block does not have a signature. However, user A does unlock the output for the Genesis block so that he can gain access to the 100 tokens. Then when user A sends the 10 tokens to user B, a signature is created for the input for block 1, which corresponds to user A's private key, and that input tells this output that it has permission to unlock and become spendable, which then allows it to generate the next two outputs, which become locked, one by user A and the other one by user B. Then when user B sends 10 tokens to user C, his output here becomes unlocked because of the signature inside of this input, and then the output here becomes locked by user C. There's one thing to keep in mind about all of this. With our current blockchain implementation, every transaction creates a single block, so we can't have more than one transaction inside of a block currently, and that's simply because the mining of the block is synchronous with the creation of the transaction. So when a user creates the Genesis block, he immediately mines it, and then when a user sends tokens to another user, he immediately mines a block, and so on and so forth. This is mainly done because we do not have a network stack, and so the mining of the actual blocks is not separate from the sending of tokens and stuff like that. For our blockchain, the way this is going to work is each input on the transaction will store a public key, which is not hashed, and then a signature of the entire transaction. And the idea is that the hash of this public key, which is inside of the input, will have to match up with a referenced output. So the output will have a hash of a public key directly inside of it, and then the input will also have a public key which is not hashed, and then we'll have a method of hashing it to check that they both correspond with one another, which will allow us to unlock the output. Let's go ahead and edit our transaction output and input structures so that they can correspond with this new format. The transaction output will have the value, which will be the amount of tokens inside of it, and then it will have the public key hash, which will lock it. Then for the transaction input, instead of having a sig field, we'll have a signature field, which will be a slice of bytes, and then we'll have the public key field with a public key that hasn't been hashed, which will also be a slice of bytes. Of course, these methods down here are now invalid, so let's replace them with new methods. Let's start by creating a method called useSKey for the transaction input. We pass in a public key hash, which will be a slice of bytes, and then we go and we get a public key hash by hashing the input's public key field using our wallet public key hash function. And then we want to compare the locking hash that we just got with the public key hash which is being passed into here. For the transaction output, we want to create a lock method which will lock the output, and this will take in an address which will be a slice of bytes. We'll take the address, we'll decode it with our base 58 decoder, which is of course in our wallet module. Then we need to remove the version byte and the checksum from the hash, and then we'll take the public key hash and assign it to the output's public key hash field. We can create a second method for the transaction output, which checks to see if the output has been locked with a key. And for this, we can simply just pass in the public key hash and then check to see if the output has that public key hash inside of it and if they are the same. So the output is locked if it contains a public key hash, and we can unlock the output if the public key hash of a user that we're passing in is the same as this transaction output's public key hash. While we're in this file, we also want to create a function called new transaction output. This takes in an integer and then the address is a string. We create a transaction output with the value inside of it, and then we put nil into the public key hash. Then we take the address, cast it as a slice of bytes, and pass it through the lock method to populate the public key hash field for this output, and then we just return the transaction output. The main reason why we're creating this function is so that we can lock the outputs that we create, but it's also because when we pass in an address, it's being passed in as a string from the command line, so we need to convert that string into a slice of bytes. While we're at it, we need to create some new methods for our transaction structure. First, we need to create a serialize method, which will take our transaction and serialize it into bytes. And this is exactly like the block serialize method that we have inside of our block file. We can use this method to create a hash method for our transactions, which will take our transactions and create a hash, which we can then use as the transaction ID. So at the top, we'll create the hash variable. Then we'll take the transaction pointer and create a transaction copy. We'll empty out the transaction's ID, and then we'll take the transaction copy and serialize it using the SHA-256 algorithm. We'll then hash it, and then we'll return that hash. Now let's create the methods which will allow us to sign and verify our transactions. So here we have a method called sign, which takes in the private key, which is type ECDSA private key. And then it takes in a map of the previous transactions, where we have a hash of the transaction as a string, which is the key, and then the value is the actual transaction. First, we want to check to see whether or not the transaction is a Coinbase. If it is a Coinbase, we just return because we don't need to sign the Coinbase. As I mentioned before, the way that we need to sign our transactions is through the actual inputs. We use these inputs to access the referenced outputs, and that's how we sign our transactions. So we need to iterate through all of the inputs and make sure that they're valid, and we can do this by checking to see if our map contains the input's ID and it's not equal to nil. So we use hex encode to string, we pass in the input.id, and we pass this in as the key, and then if the value's ID is equal to nil, then we want to panic and say that the previous transaction does not exist. Next, we need to create a transaction copy, and to do this we're going to use a method which we'll create called trimmed copy, which will create a copy of our transaction. While iterating through the inputs of this copy transaction, we want to do a few things. In each input, the signature is set to nil, and this is sort of just a double check. We just want the signature to be equal to nil. The pub key field is set to the output's pub key hash. And the idea is that all of the transaction but the current one are empty, so their signature and pub key fields are set to nil. Thus each of our inputs are signed separately, which is sort of the point. Then the hash method serializes the transaction and hashes it using the SHA-256 algorithm, and then pushes this hash into the transaction's ID. This ID is the data that we're actually going to sign. Then after we get this hash, we want to set the pub key field on the input to nil. The main piece of this function is this part here. We call ECDSA sign, and we pass in a random number generator. We pass in a reference to the private key, which we're passing into the function, and then we take the hash data which we pushed into the TX copy ID, and we sign it. This signature gives us back two different numbers and a potential error, so we need to handle the error. We can take the two numbers, convert them into bytes, and then concatenate them together to give us the signature, and then we can put this signature into the signature field of our input. Before we make our verify method, let's make our trimmed copy method. This just is called on a transaction, and it outputs a transaction. We want to make two arrays, one for the inputs and one for the outputs. We'll iterate through all of our inputs, and we'll take and we'll put all of the inputs into our inputs array. Then we'll iterate through all of the outputs, and we'll take all of the outputs and put them into our outputs array. Now notice for the inputs, we're taking the in ID and the in out, and we're then clearing out the pub key and the signature. And then finally, we're creating a transaction where we're copying the transaction ID and then the inputs and the outputs. And this is the transaction copy that we're using in the signed function. Now let's go ahead and verify each of our transactions. This method takes in the previous transaction's map, and then it outputs a boolean. We check if a transaction is a Coinbase, and if it is, then we automatically verify it by returning true. Again, we want to iterate through each of the inputs and make sure that they exist. We then need to grab the transaction copy using our trimmed copy method. Then we want to reconstruct the curve that we used to generate our key pairs by using the elliptic P256 function. We want to iterate through each of our outputs and check the signature in each of our outputs. And we can do this through these steps. This part is identical to the piece inside of our sign method because during verification we need the same data that was signed. So we need to create the transaction copy that was hashed from before. So again, we're going to make the signature nil, then we'll make the pub key equal to the pub key hash of the output, then we'll create the hash and push it into our transaction copy ID, and then we'll take the pub key and make it nil. We then need to unpack all the data that we put into the signature and the pub key of the transaction input. And since each of our signatures is just a pair of number and our public key is just a pair of coordinates, we can deconstruct them back into those numbers and coordinates. So we'll create the RNS for the signature. Then we have the signature length by just calling input signature and length on it. We then want to just divide the signature in half, with the last half being the R and the first half being the S. And then for the public key, we'll do the same thing except for X and Y. We use ECDSA to create a new public key by using the X and the Y that we extracted and the curve that we created up above. Then we can execute ECDSA.verify by passing in the public key, the data that we hashed, and then the R and the S. And if this verify comes back as false, then we just return false. If all of the inputs come back as verified, meaning all of these pass this test, then we want to return true from this function. There is one more method that we want to create inside of our transaction.go file before we move on, and this is just a method to convert our transaction into a string representation so that we can see it in the command line. And I'm not really going to go into detail about this method. You guys should go ahead and take a look at it yourselves. We're just using sprintf to create a bunch of strings, and then we'll print all of these out based on the outputs and the inputs in our transaction. Alrighty, so now let's move over to our blockchain.go file and create a few methods for the blockchain, which will allow us to find transactions, sign transactions, and verify them. So with the find transaction method, we want to pass in the ID of the transaction that we want to find, and this will pass back a tuple of transaction and error. We'll use our iterator to iterate through our blockchain, and of course we'll create a for loop where we call iterator next inside of it, and then if the length of the block previous hash is equal to 0, we'll break out of the for loop. For each of our transactions inside of the blocks, we just want to compare the transactions IDs with the ID that we're passing into here, and then if we get a match where the ID and the transaction ID compare with one another, then we want to return a pointer to that transaction and then nil for the error. If we iterate through all of our transactions and don't find one that matches the ID that we've passed in here, then we just want to return back an empty transaction and then an error that says the transaction doesn't exist. Now let's create the method to sign the transactions. This will take in a transaction and then the private key, which is the ECDSA private key type. We'll first make a map where we have the string being the ID of our transaction and then the value being the actual transaction itself. Then we'll iterate through all of our transaction inputs and we'll call our find transaction method on the input ID. If we get back an error, we want to handle it, and then we want to take our previous transactions map, encode the transaction ID into a hexadecimal string to put into the key of the map, and then put the actual transaction that we're finding inside of our blockchain into the map. Afterwards, we'll call our sign method on the previous key and then our previous transactions. So it will go through the map that we're passing it and sign all the transactions independently. The verify transaction method will do roughly the same thing, except this time, rather than signing the transactions, we just want to verify them. So again, we make our map, then we iterate through all of our inputs, we find all the transactions, and then we put all the transactions into the map, and then we pass the map to our transaction verify method, which will return a boolean, as you can see here. And that's really all we need to do to add all of this stuff to our blockchain. Now let's go and clean up the errors that we created by changing our transaction input and output struct and removing those old methods. For the find unspent transactions function, we need to pass in a slice of bytes, which will be our public key hash, rather than a string, which is the address. Then for anywhere where it was referencing the address, we need to replace it with the public key hash. And then for the places where we had our old methods, we need to replace them with our new methods. So for output, we want to call is locked with key, and then for input, we want to call uses key. We'll repeat the same process for the find unspent transaction output method. So again, replace the argument here with a slice of byte called public key hash, and then replace the can be unlocked with is locked with key method. And finally, we want to do the same for the find spendable outputs function. So we turn the address into the public keys slice of byte, and then we pass the public key slice of byte into everywhere where it was address, and we change the output method into is locked with key. Inside of our transaction.go file, we need to replace all the places where we're creating transaction inputs and outputs. In our Coinbase transaction function, we just replace it with our new transaction input, which has 4 fields instead of 3, and then we replace the output with the new transaction output function. And this will cause an error here, so we just want to turn this into a pointer. Down inside of the new transactions function is where we're going to be connecting our wallets module. So we want to call wallet create wallets, and then handle a potential error that comes from here. And then we'll call get wallet with the from address string inside of it. And then we want to get the public key hash of that from address string. Then where we're calling the find spendable outputs function, we'll replace the from string with the public key hash. And then down where we're creating the transaction input, we need to replace the old one with 4 fields, and the final field will be the public key of the wallet that we instantiated. Then where we're creating our outputs, we want to call our new transaction output function with these same values inside of it. And then the only real major change is down here. So instead of calling the setID function, we want to call the hash function. So our transaction ID is now equal to transaction hash. And then we call sign transaction, and we pass in our private key. And this, of course, now sort of binds everything that we did in this tutorial with the stuff that we did in the last tutorial. There are some minor things that we want to change inside of our command line interface. So we want to print out all of our transactions. So in the print chain command, we'll come down here, we'll iterate through each of the transactions in the block, and then we'll call fmt println transaction. Then the get balance command needs to be changed slightly. So before we were just taking the address string and passing it in to this find UTXOs function, and now this takes in a slice of byte. So we need to take the address, decode it using our base 58 decoder, and then get the public key hash and then pass it into the find UTXO function. We also want to create a little if statement which validates the address that we're passing through, and then if the address isn't valid, we just pass back that it isn't valid. And we'll put a little if statement like this inside of every single one of the commands where we're actually passing in an address, which includes the create blockchain command as well as the send command. And with the case of the send command, we need to create two, one for from and one for to. Now let's go inside of our command line and see if all of this works. First we need to create a new wallet, and actually I'm going to create two wallets so that we can send and receive tokens back and forth between the two wallets. Let's then create the blockchain with one of these addresses, and of course the address that we create the blockchain with will get the mined tokens for the Genesis block. That seems to have gone well, so let's now print the chain and take a look at the transactions inside of our Genesis block. And here you can see what it actually looks like. So here's the hash for the Genesis block, the previous hash, and then the proof of work, and then the transaction hash, followed by the first input, where we have the TXID, the output, the signature, and the pub key, and then the actual output, which has the value, and then the script. Now let's create a new block where we're sending from the account that has the tokens in it to a different account, and we'll send the amount of 30 tokens. And once that's done, we can go ahead and print the chain again. And you can see here we get our Genesis block first, and then we have the actual transaction of the second block in our chain. So here we have the input with all of its data in it. It has a signature and a pub key, and then we have two outputs. One of them has 30 inside of it, and then the script, and then the other one has 70 inside of it, and then the script. The one with 30 is assigned to the user that we sent the tokens to, and the one with 70 is the one that's assigned to the user that sent the tokens. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you dislike this tutorial, then by all means, downvote it as much as you like. Have a good night.